Yeah? You're engineer. Okay. Yes. He's a good engineer. I count on him. Here's the batteries. Oh.
What is it?
This one? No. Maybe. It's working, so we will. Okay. Okay, we'll check. But we'll find it. Probably it's somewhere below.
Oh, here it is.
Very good. So why don't we see on the projector? Again. Oh, okay. So. Okay. Thank you. Okay. Sorry. Sorry. Thank you. Okay. Okay. Hi. Good morning. Okay. So I hope you enjoyed the quiz. So it was actually without any mathematical derivations, just to give you some questions to check yourself about the understanding of the concepts. So let's go quickly through the questions. You can see first question. Using the MVDR filter, we can obtain a higher noise reduction factor when, which one is true? It's correct? I didn't hear. A, B, C, D. A. Okay, good. Because when Rx, the rank of Rx is smaller, so the noise subspace is larger, so we can reduce more noise and we get higher noise reduction. Good. To increase the output SNR, we need A, B, C, D. Okay, let's check it. C, to increase the output SNR. So if we decrease L, the output SNR will be higher or lower? What is the effect of L on the output SNR? So which one do you think is correct? You said C, D, D. Okay, D. If we increase L, we use more information because we use the correlation between any two samples. When we increase L, we can use more information. That means the correlation between distant samples. That's why we can increase the output SNR. Actually, when we increase L, what happens to the mean squared error? Decrease. So both the SNR, output SNR increases and the MSC decreases. Okay, let's move on. The desired signal distortion index that is obtained with the MVDR filter, A, B, C, D. D, smaller than the noise reduction factor. That's true, because the desired signal distortion index actually is 0 for the MVDR. So it's smaller than the noise reduction necessarily. The noise reduction is positive number. Okay, the gain in SNR, A, B, C, D. Which one, C or D? Or C, okay. The ratio, let's read it, the ratio between the noise reduction factor and the desired signal reduction factor. Okay, but even if you don't remember, think about, okay, so maybe you remember it's some ratio, but you're not sure if it's C or D. Okay, let's think about it. And the noise reduction factor, when you increase the noise reduction factor, it means that you suppress more noise, right? So what happens to the gain in SNR? Increases. Exactly. So it should be in the numerator. Okay, so it's the ratio between the noise reduction factor and desired signal reduction factor. Okay, let's move on. 5. Low SPCC between V and Y indicates A, B, C, D. B, let's think about it. Okay, so the squared person correlation coefficient, if it's low between V and Y, what does it mean? If it's low, it means that the noise is low. Okay? If the noise is low, it means that the input SNR is high. So it's B, high input SNR. Okay? 6, to increase the noise reduction factor, which filter do we need to choose? Which one? B? Okay, so B, trade-off filter with mu larger than 1. Is it correct? What about maximum SNR filter? So the maximum SNR filter actually achieves the maximum noise reduction. Okay? So maybe it's confusing, which is true that we can use the trade-off, but the maximum SNR, it can increase as much as possible because it increases the output SNR, which is achieved by maximizing the noise reduction factor. Okay? 7. So even if you made mistakes, it's fine, you know, it's just to practice the terms and so on. High SPCC between X filter desired and Z indicates A, B, C, D. What? C. Let's think about it, of course. So if we, when we talk about correlation between X filter desired and Z, it relates to the output SNR. So we can remove B and D, okay? And if it's high, it means that the output SNR is high, right? So it's A, okay? because if these correlate, high correlation, it means that the output SNR is high. So it's A. The next one, 8. Using the Wiener filter, when the input SNR increases, A, B, C, D. What do you think? B? Okay. Which one? Last one, D. Okay, let's see. Okay, so using the Wiener filter, the input SNR increases, so the noise reduction factor decreases, and the desired signal reduction factor decreases. So both decrease. Okay, so if the input SNR increases, it means that we have less noise in the input. So if we have less noise at the input, the Wiener filter doesn't need to work much. So it's less aggressive. So it reduces less noise, which means that the noise reduction factor decreases. Okay, good. What about the desired signal reduction factor? Also decreases because we have less distortion because the input SNR is high. So it's D, correct. 9. The MVDR filter can be derived by A, B, C, D. Okay, let's check C. Okay, so the MVDR with C, it's minimization of JNH subject to this. Okay, so we can remove A and B because the MVDR is distortionless. So it doesn't minimize JD. It minimizes JN, the variance of the noise, or the MSC that is related to the noise. So it's either C or D, according to this, the beginning. It minimizes JN. Now, regarding the constraint subject to, so this is the signal subspace. So this is the distortionless constraint. So C, correct. Okay? Number 10. To find the maximum SNR filter, we need to compute A, B, C, D, D. Okay, the D, the maximum eigenvalue of RV minus 1 Rx. Okay, correct. Okay, so a simple quiz. I hope you enjoyed. Okay, now I'll show a short video. This one. It's from the IEEE Signal Processing Society. I hope it works. Okay.
Have you ever wondered, how do Amazon Echo and Google Home understand my questions? The answer is signal processing, the science behind our digital lives. Computers and smartphones have allowed speech recognition for quite a while, but deploying that technology in home assistants has been much trickier. With smartphones, commands are often spoken very close to the microphone, whereas with home assistants, commands are often spoken anywhere within a large room, which is much farther from the microphone. This means the device must process not only speech, but also echoes and conflicting noise that deteriorate accuracy, including the TV, kitchen appliances, and other people talking. Utilizing a trick
Somehow was removed. Maybe the light to dim the light, or maybe if it's okay, it's okay. Well, but is it okay? Okay. Is it visible? No problem? Okay. Sorry, it went out.
Often spoken very close to the microphone, whereas with home assistants, commands are often spoken anywhere within a large room, which is much farther from the microphone. This means the device must process not only speech, but also echoes and conflicting noise that deteriorate accuracy, including the TV, kitchen appliances, and other people talking. Utilizing a trigger word like OK Google or Alexa activates the Home Assistant to recognize a command or question. Once the device is active, it sends all following speech and sound streams to data servers that process the request. The wide variety of conflicting noise results in extremely complex sound waves, making it more difficult for the Home Assistant to understand, process, and respond to commands embedded within. For devices like Amazon Echo and Google Home to successfully analyze complex speech waves and determine the embedded command, they use far-field speech recognition, whereby signal processing engineers conduct specific machine learning techniques. Far-field speech recognition can be enhanced in two ways. The first is multi-channel speech processing, which uses multiple microphones to allow signals to be enhanced from some directions and suppressed from others. Next time you use your Amazon Echo, notice that it purposefully lights up in the direction in which you're speaking. The second is multi-condition training, which trains the device to find the command within all the sound waveforms, including the speaker's reverberation, others talking, as well as TV and kitchen appliance noise. This statistical model is trained from a myriad of examples. To ensure accuracy, signal processing engineers create countless situations where sound waves are emitted and picked up by microphones in different areas of the room. Google, for example, uses a room simulator to generate such signals from various rooms that are small, big, noisy, echo-prone, and more. Combining multi-channel speech recognition and multi-condition training to achieve far-field speech recognition allows signal processing to decipher complex speech waves and fuel this new wave of Home Assistant technologies. We owe much of that success to advancements in signal processing and machine learning in just the past decade. Will you be part of the next wave of signal processing fueled technology? Visit us online to learn more.
Okay, so I just also want to mention that this year, the main conference of signal processing, ICASP, it's going to be in Hyderabad in April. So it's very close and first time in India. So I hope you will have the opportunity to attend this conference, to see some demos, some lectures on different kinds of signal processing, array processing, and so on. Okay. Okay, before we continue, do you have any questions about the material we've gone so far? Okay. So today we will continue with single channel signal enhancement, but instead of the time domain, in the frequency domain. And yesterday we talked about motivation, why we need to work in the frequency domain, what are the advantages. So there are advantages to work in the time domain. There are also advantages to work in the frequency domain. Depends on computational complexity, the length of the filter, and actually the problem in the environment. So similarly to the time domain, single channel signal enhancement, we will describe the signal model, problem formulation. We'll talk about noise reduction with gains. We mentioned yesterday that it's possible to do noise reduction even with vectors that take into account the correlation between frequency beams. But we will neglect that to make things simpler. Of course, you can extend it. But then, the more information that you use, you need to estimate or to obtain this information reliably, which is not a simple task. Okay? We will talk about performance measures, similarly to the time domain. And then when we have performance measures or criteria, we can derive optimal gains. Lastly, we will, you know, that we don't work in the frequency domain, we work with windows. So we will extend it to implementation with a short-time Fourier transform domain. And then you will also get assignment today, and you will have also an opportunity to practice with speech enhancement. So you will be able to record your own voice, to add noise, to hear it, how it sounds, and then to do speech enhancement, which means to reduce the noise and to verify what is the trade-off between noise reduction and signal distortion. Okay? But I don't want to give you too much homework. It's up to you. Okay? So I'll give you an assignment, and the other one will be an extension with a short-time Fourier transform. Whoever wants to do something beyond the assignment, I will describe what you can do, and then you can also practice this like a real problem. You know, it's fun, for the fun. Whoever wants to extend and has some time. Okay, so I hope all of you that submitted the first assignment, if you had any problem or question regarding that, please ask today. Maybe after we come to the second assignment, and if you have questions, we can talk about it, okay? Because it's important that you practice. I hope that with the MATLAB code, you didn't just take it as is and change parameters, but also to read how it looks like. It's also, you can keep all the MATLAB codes from the book. I also sent some chapters that related to this material. And it's useful, actually. Suppose that you want to do use this MATLAB code for other problems. So it will give you the basics, how to implement things that we learned in class based on the mathematics, how to implement it using a MATLAB code. It's very important. And then you will be able to write your own code with things which are more sophisticated, okay? Especially when we will talk about the implementation in the short-time Fourier transform. Okay, we will talk about details which are important, and they are implemented in the MATLAB code and how to do that. So I really encourage you to also to practice and read the MATLAB code and understand it also in this part, which when we reach that, okay? Even if you don't have time during this period of time, this week, you can do it afterwards. But it's important. Okay. So we start in the time domain. This is the model, just like we had in the time domain, but instead of working in the time domain, we transform the signals to the frequency domain, and then we have this problem. Y equals to XF VF. And as we said, that we want to simplify the filtering as much as possible, which means that we want to estimate X from Y alone. This is interesting, okay? So we have YF equals to XF plus VF, and we want to estimate XF using Y from the measurement YF. So you remember that when we talked about the time domain filtering, we said it's very difficult to estimate a single sample from a single noisy sample because we don't know how to separate it. And here, we actually use a single frequency estimation of the clean signal from a single frequency noisy measurement. Okay, so what kind of information can we, do we need? How to do that? Is it possible to do that? Maybe we require information that is not available. So we have these questions. So you see, we work here in a more simple way to estimate the desired signal. And we need to know if it's possible or not. Okay? We need to think about it. What kind of information? Can we obtain this information from noisy measurements? Okay, so ask questions. Okay. Once we have this, we can do the inverse Fourier transform and go back to the estimate of the signal in the time domain. So we work, when we go further, we will move to windows. But for now, we assume we work in the Fourier transform domain, and we work with stationary signals. Okay, so we don't need windowing, and the length of the Fourier transform can be as large as we want because the signals are stationary. Okay, so we can define the variance of the measurement, the noisy measurements in each frequency. So actually, if we work on each frequency independently, we can actually remove the dependence on F, okay? Because we work on each frequency independently. So sometimes we keep the function of F, and sometimes maybe we can just drop it because we understand we work on each frequency independently. So here, YF is a scalar, right? So it's a complex scalar. And the variance of this complex number is defined like this. So this is its variance. And we can write it as the summation of two variances, variance of X and variance of V. So see, when we work on scalars, everything is much more simple. Let's continue. If we do noise reduction with gains, it means that we need to find filter in the Fourier transform domain. So we multiply each noisy coefficient with a certain generally complex number. And then we achieve the enhanced signal. So you see, if we multiply with a certain H, for each frequency, it's different, okay? Different gain. That's why we call it gain, because it's not even a filter. It's just a filter in the time domain. It's also a gain in the Fourier transform domain, okay? So we can just multiply it with different gains, and then we get two components in the estimation. One is filter desired, H multiplied with F, and the other one is the residual noise. So on one hand, we want that X filter desired will be equal to X, which means that the gain H should be 1. Ideally, we want to have this H multiplied with X to be equal to X for any X, for any desired signal. So ideally, we want HF to be 1 to reduce distortion. On the other hand, we want the residual noise to be as small as possible, low. So we want H to be close to 0 to suppress more noise. So the value of H depends on the performance measures. What do we want to achieve? And we can understand that if the input SNR is very high, probably we would like H to go as high as possible, closer to 1. Okay? So we can think of even like this. Makes sense that even that h can be a complex number, right? It can be a complex number because we work in the Fourier transform domain. It makes sense that h from here, it will be between 0 and 1. Even a real number, it can do a good job. I don't say that we restrict that and we are looking only for real number, but I say that it makes sense that if we want to reduce noise, maybe it's between 0 and 1. So for each frequency, suppose that we know for each frequency the signal-to-noise ratio. Then if the signal-to-noise ratio for each frequency is high, then we will multiply it with a gain that is closer to 1. If the input SNR in that frequency is low, we will multiply it with h that is close to 0. Okay, so suppose that you have a signal, desired signal, you transform to the Fourier transform, you have some frequencies where the signal is strong, the desired signal is strong. So in the other frequencies, if you don't have desired signal, h in those frequencies will be 0. And in frequencies where the SNR is high, h will be closer to 1. If the SNR is low in some frequencies, h will be lower. So you can get noise reduction, total noise reduction, especially in frequencies where you don't have the desired signal or where the signal is weak compared to the noise, so you want to reduce that. So the distortion using a gain like that will come from weak or low SNR frequency components, okay? Because when we reduce, when we have a gain like this, of course we will put low gain in frequencies where the SNR is low to minimize the distortion of the desired signal. Okay, so all this makes sense. Let's continue. If you have any question, please ask, okay? Okay, so the X filter desired is simply H multiplied with F, and the residual noise is H multiplied with V in the frequency. So the variance of the signal estimate is a summation of two components. One is the variation of the filter desired, and one is the variance of the residual noise. Okay? So we want to keep the filter desired, but we want to suppress the residual noise. And it looks like this. Okay, so it's simply multiplication with the HF magnitude squared. Now let's define performance measures. Okay, so of course it's always good to define the input and output signal to noise ratio, which will give us the gain in SNR. So we define the narrowband input SNR. Narrowband, it means that we compute the performance measure for each frequency. So we have narrowband. And then we have also broadband. It means that we compute this performance measure across all the frequencies. Okay? So the narrowband input SNR, it's a function of f because we compute it for each frequency separately. And then we have the variance of x, divided by the variance of the noise for each frequency. If we want to compute the broadband input SNR, so we compute the total variance of x over all frequencies in the numerator, divided by the total variance of the noise over all frequencies. Okay? You see, when you compute the broadband, you don't put the integral here. but you put the integral in the numerator and the denominator, because this gives us like the energy of the signal divided by the energy of the noise. So this is the input signal to noise ratio. The output SNR, we compute it for here, okay? So here, we can write it as X filter desired plus V residual noise. So the variance of X filter desired divided by V residual noise, we obtain the narrowband output SNR. So we see that the narrowband output SNR is the same as the narrowband input SNR. Why? Because using a gain, if we just use a gain for each frequency, scalar gain, we cannot change the narrowband SNR. So the output SNR, the narrowband output SNR is the same as the narrowband input SNR for each frequency. But still, we don't care much about the narrowband SNR. We want the output signal in the time domain to be with higher SNR, which means that we care about the broadband output SNR. So the output SNR, the broadband output SNR, we need to compute the energy of the filter desired signal over all frequency divided by the energy of the noisy residual noise at the output of the estimator. So we have this expression. So we can ask ourselves, of course, we cannot get any gain in SNR for narrowband, in the narrowband for each frequency. But the total, the broadband output SNR, can we choose H for each frequency such that the broadband output SNR will be as high as possible, for example? We will see how to do that, okay? How to choose or H for each frequency, okay? So you see that if I give you an example, suppose that I have desired signal, and the desired signal, the signal to noise ratio in each frequency is different, okay? So when I multiply each frequency by a certain number, complex number or even real number, I cannot change the SNR in that frequency. But if I keep the high SNR, so H, the gain is high when the SNR, the narrowband SNR is high, and is low, H is low, the gain is low, when the input narrowband SNR is low, I will get higher broadband output SNR. Okay, because I take the integral. And you can think about it like this. Let's think about, just for simplicity, that the variance of V is constant for all frequencies. Okay, suppose that it's constant for all frequencies. Which means that the noise is white, right? It's the same variance for all frequencies. Just to think about it. So here in the denominator, we will have the integral over magnitude. So it's the norm of H. We just take the summation of magnitude squared H over all the frequencies. So suppose that we want to normalize H. This will be constant. Okay, so suppose that we would like to find H for each frequency, and we normalize it, which means that the denominator is always constant. So we can ask ourselves, if we want to maximize the output SNR, we need to choose a vector H, it's a vector because it's for all frequencies. Okay, so it's a vector from frequency 1, 2, and so on. Or if you start with frequency 0. Okay, so it's a vector that contains all the gains for all the frequencies. So we need to find a vector, and we can normalize it generally. Okay, so we don't care about the denominator because it's anyway normalized such that the norm is constant. And then we need to find this vector H such that the numerator will be maximized. How do we do that? How do we maximize this numerator when the norm of H is constant? How do we do that? Okay, this integral. Okay, so I think you know how to solve it, but even without solving it mathematically, think about if I take a vector of H, that is norm is constant. It means that if I increase one element, I need to decrease other elements. One, because the norm is constant. Okay? So for which frequencies I will choose to make it high and which frequencies is constant. So if I increase one value of H, I need to decrease other values. So in order that this integral will be larger, what do I need to do? It's better for me to take higher H when phi x is high, because then the integral will be higher. Which means that when the signal, this is higher, we said that this is constant, okay? Just for the example, I try to simplify things so you get intuition. So this is higher when the SNR is higher for white noise, okay? So when this is higher, we will choose H to be higher. When this is lower, we can make H lower. And then this integral will be total value higher, even that the norm of H is constant. Okay, but generally, if it's not white noise, it's very similar to what we did in the time domain. So it's based on the signal-to-noise ratio. So when the signal-to-noise ratio, we will choose high H. When the signal-to-noise ratio is low, we will choose lower H. Just like in the time domain, we took the first eigenvector of RV minus 1 Rx. Similar things, but here we don't need eigenvectors because it's just the ratio for each frequency independently. So it's even simpler. Okay? Noise reduction factor. So noise reduction factor, it means the ratio between the original noise, the variance of the noise in the input, divided by the noise at the output. So we get this ratio, which is 1 over magnitude squared of H. If we talk about, this is the narrowband. If we talk about the broadband, so we need to take the integral here divided by the integral in the denominator. Because this is the total variance of the noise at the input, and this is the total variance of the noise at the output. Okay, make sure that you don't take integral here, because this was reduced. Okay, so you need to take the integral here. You need to keep variance of V in the numerator and denominator, then take the integral. Okay, of course, because we understand that we take, it's the energy, the total variance of the noise, the input and the output. This is the noise reduction factor. This is narrowband and broadband. Desired signal reduction factor is the ratio, this is the narrowband, desired signal reduction factor, which is the variance of X divided by the variance of filter desired. So it's similar to the noise reduction factor, the narrowband, because it's just the ratio, because we use a scalar gain. But the broadband is different, because we take the total variance of the input desired signal divided by the total variance of the desired signal at the output. So we have this ratio. And we want, just like in the time domain, we want the noise reduction factor to be as high as possible, which means that we reduce as much noise as possible. And the desired signal reduction factor, we want to have to be close to 1. If it's high, it means that we have more distortion. If it's close to 1, it means that we have less distortion. And we have this ratio similar to what we had for the time domain. You see, so these ratios are for the broadband measures. So the gain in SNR, the broadband gain in SNR is the ratio between the broadband noise reduction factor and the broadband desired signal reduction factor. Just like what we had in the time domain. You know, now after the quiz, you remember all the terms, so it's much easier to continue because you're familiar with the similar terms. Okay, let's talk about the distortion index. Okay, so the desired signal distortion index, it means how X filter desired is different than X. And we normalize it. Okay, so we take this difference, X filter desired minus X. We take the magnitude squared and expectation, and we normalize it by the variance of X. So we see that for the narrowband distortion index, it looks like that. It's 1 minus H magnitude squared. For the broadband distortion index, we need to take the integral in the numerator and the integral in the denominator before we cancel out the variance of X. So we have this expression. And of course, this distortion index is generally between 0 and 1, and we want that it will be as close as possible to 0, which means that the desired signal is undistorted. By the way, this morning we had a quiz, so people who came afterwards, they can still do the quiz after when we have a break, okay? It's just for you to practice, so it doesn't really matter. It's not like a grade that you need, but it's nice to see that you're familiar with the terms. Let's continue. Mean squared error, which is a very important performance measure. By the way, we like mean squared error many times. Why? Because it's usually it correlates with the performance of many applications. Because if the mean squared error is low, it means that the performance is better. But generally, it's not always true, but this is one thing. But also, it's many times in many applications, we can derive explicit expressions for the estimators or different things using this mean squared error criterion. So we can derive explicit mathematical expressions. That's why people like it. But if you use deep learning, for example, also there, people choose performance measures that correlate better with the performance of the algorithm. You know, the performance of algorithm depends on the application. What do you want to measure? For example, suppose that you have automatic speech recognition, ASR, and you have application just like I show in the video. and you want to speak to home device. So you can measure what is the error rate, the word error rate when you speak on the average. And then for speech recognition, you can measure that, and so on, for a specific speech recognizer. And for images, you can measure different criteria, different errors on the images. It depends if it's what the purpose of the images are. For example, if the image is just to show on screen on the phone, or is it for medical applications? It's totally different performance measures. And then if you try to enhance signals for specific applications, you need, and you use deep learning. You know, with deep learning, you don't need explicit mathematical expressions for the derivations or even algorithms. You just train a network and you find the parameters. But even then, you cannot take any performance measure. Usually, in order to train the network, you need that you will be able to find derivative of the performance measure. Why do we need to find derivative of the performance measure? Do you know? Are you familiar with deep learning, or do I go, because probably some people are familiar with deep learning, so I want to give the insight, how we use also deep learning. So for deep learning, we use training data. And then we have parameters of the network. So suppose that we have, like here, y, so it can be yt, or in the frequency domain, maybe. And then we have a network that it does something, and then the output will be zt. Or in the frequency domain, it will be the f. Usually in the frequency domain, we need all the frequencies. So this network or model, okay, so it will be a model, neural network model. It means that we have parameters. And we need to find parameters based on what? Based on training data, okay, because this is what I have. And how do I find the parameters of this model? Based on the performance measure, based on the criterion that we want to optimize. So using gradient descent, you know, when you optimize something, usually you want to do it in an efficient way because you don't have optimal solution. So you find a solution and you guess a solution, or you start from a certain point, and using gradient descent, you become closer and closer to the optimal solution. What is the optimal solution? The optimal solution of these parameters will be minimum of something, of the performance measure. For example, if you want to minimize, minimum of the performance measure that you want to minimize for the average based on the training data. Okay, so you optimize. So you find the parameters that minimize the performance measure, the average value of the performance measure, using the training data. This is what you find. But you need to do it efficiently because you don't know what are the parameters. So each time you come closer, closer. So these methods of coming closer to the solution, they are called gradient descent. If someone is not familiar with gradient descent, urgently today go read about it. Okay, so it's very important. I guess graduate student engineers, probably you are familiar, you're well familiar with that. And what are the benefits, how to optimize. Usually with gradient descent, you change also the jump, how close. Because at the beginning, you want big jumps to come closer to the optimal solution. And when you come closer, you need to decrease the step size. Okay, all of that. And if you want to learn more about it, it's with adaptive filtering, adaptive processing, and all that. So neural networks, this theory was developed for many years, decades, from the 60s of the past decade. It's not new, but now it became very popular, especially in the last 20 years. You know why? Why it became popular in the last 2 decades compared to previous years? What? Data, very good. Data, which means that we can collect a lot of data in memory. So memory is cheaper. And what else? Processing units, yes. So to process data or to find the optimal parameters of this. Sometimes these models contain millions of parameters. So think about to find the optimal values of these millions of parameters, it takes a lot of processing. So it became cheaper. Are you familiar with the first application of neural network? I think it's a massive usage. I think maybe it's one of the first application of neural network. Are you familiar with that? Which one? What do you think? When was it and what was it? When and what? Okay, the theory was much earlier, but what was one of the first applications that was very massive usage? What? ESR? No, speech recognition actually much later. Speech recognition in the last decade. Okay? What? Classification of objects. What kind of classification on which object and when? Just a minute, what? Yeah, objects and images, okay. But what kind of objects? When was it? Okay, you come close. But when do you think was it? And I tell on massive usage. Okay? Yes, number recognition, which is similar. When was it? In the 90s. 98, more specifically. Okay? In 1998. So a long time ago. And then there was a challenge, and actually it was made for usage by in the industry. So back then, for example, in the United States, people wrote numbers by handwritten numbers on envelopes. So it was zip code. And then think about to recognize the numbers. Each person writes the number differently. So what they did, and people that write the numbers, so it's possible to take a small image, maybe 32 by 32 pixels, and the numbers, which contains the numbers, the envelope. And then inside this small image, maybe 32 by 32, you have only, we can assume that the numbers are not connected. So each image like this contains a single number, single digit, which is nice. So we have classification. So we have an image, okay? So here we can have an image, let's say Y, that is 32 by 32 pixels. And the output, let's call it, this will be a neural network. And the output will be R, which is 0, 1 to 9. So we need to know what is the digit for handwritten digits. And think about each person, if you want to do it using some signal processing, so to take images, and an expert needs to think what are the features of the numbers, how to discriminate between this digit and another digit, and so on. So the images here are binary, which simplify things. Okay? And then it came out that for a certain neural network, actually it's quite simple, neural network, it's possible to find the features of the image, and also if you shift the digit in the image, it doesn't affect. So it's shift invariant, and then we need to classify or to find which digit it recognizes. Okay? So in addition to memory requirements, so it became easier for memory to take a large databases of many images like this for people that write different ways, different digits. And we take a large training data set that represents the whole people who wrote digits. And also computational complexity, because we need gradient descent to find the parameters of this neural network, to find the optimal, such that the classification will be more accurate. So what is the performance measure for the classification? The performance measure, what will it be? What? Okay, so we can say that this is R hat, okay? So we know for each image Y, we know the true class. What is the digit? So you suggest, so we take R minus R hat squared like this. This will be performance measure. It makes sense, right? Because this is classification error, average classification error. But this doesn't work. Actually, we want to minimize this. But this is not good. And my question is, why this is not good? What? So in terms of the application, this is a good performance measure. But I say it's not good for our problem, because in our problem we want to optimize. Does it work? Well, we want to optimize to find the optimal parameters of the network. So we need to do gradient descent. For gradient descent, we need to find derivative of the performance measure, because based on the derivative we can come closer and closer to the optimal solution. But then because we cannot find derivative for something like that, it's not good. So just before this was in the industry, this problem, there was one of the seminal innovations that was used for deep learning was backpropagation. Okay, backpropagation that enables efficiently to train the neural network, which means to find the optimal values of the parameters, and also how to replace a performance measure with another performance measures that correlates well. Okay, so instead of finding the classification error like this, it's possible to find something like, which is close like to mean squared error, which we can find the derivative derivative with respect to the parameters. And then we can use gradient descent. Okay, so we came from mean squared error, and I showed you that sometimes we use mean squared error, even though it's not the correct performance measure, but it enables us to find a good solution. Either which is derived based on mathematical solution, or even with deep learning, because we want to optimize the parameter, we need something that can be, we can find the derivative in an explicit expression. Okay? Okay, so you see sometimes we go out of the material, but it's important because you connect and these days this material is very important. Okay, so I recommend to study if you're not familiar with that. It's important. It will be useful for you. Okay, so here with the mean squared error, if we define the error between z and x, so you see the error is composed of two components. One that is related to the distortion, and one which is related to the noise. And because the desired signal and the noise are uncorrelated, this is the assumption, that here the x and v are uncorrelated. Even we can sometimes have that we can say that they are statistically independent. Okay? But for this purpose, it's enough that they are uncorrelated. We have the mean squared error. We can write the mean squared error as a summation of two components, one which is based on the distortion and one which is based on the noise, just like what we had in the time domain. Now, if we have this explicit expression, you see this is the explicit expression for the MSE. So, for example, when we talk about optimal gain, like the Wiener gain, which is the Wiener filter, we just need to find derivative of this with respect to h, just like what we did in the time domain. So the derivative and equate it to 0. But in the time domain, we had to find the derivative of a scalar function of a vector. Here, it's a scalar function of a scalar, of h. H is a complex scalar. So my question is, of course it's easier. In the time domain, it was a scalar function of a real vector. And that was also useful. So if you are not familiar with derivative with respect to vectors or with respect to matrices and so on, this is also important, something important to learn. Any textbook, maybe I can send something to read, some basics. Okay, if you're not familiar, I will send you, okay? I will send some material how to do these derivatives, because it's important for signal processing, of course, array signal processing, and also for deep learning, also very important, also for image processing. It's useful everywhere in signal processing, okay? When I reach the room, I will send you today. I will look for something from textbook. Okay, but here it's even much simpler because h is a scalar. How do we find the derivative here with respect to h? Can you do it yourself? Let's wait 2 minutes. Find the derivative of jh with respect to h, because we will want to do it when we find the performance measure. Okay? And I will do it soon. How do we do it? Derivative. Okay, so I will remove the dependence on f because I don't care, but I can write like this. JH equals to 1 minus h magnitude squared phi x plus h magnitude squared phi v. And we need to find the derivative with respect to h and equate it to 0. So we need to find this derivative. How do we do that? Okay? So something I'll remind you. How do we do that? What? Two options. Two options. Remember that h is a complex number. J omega, what? Do you want to come? Why not? Okay. So there are two options. One is the difficult option, one is the easier. So first, I can define h as the real number and the imaginary, hr plus j hi. And then, instead of something like this, do you agree that something like this, you think about that this is a single equation, but it's with complex numbers. So it's like two equations. Because I can take the real of this and the imaginary, and both need to be 0. So actually this is two equations. One for the real value, and one, when I write something, complex equation equals to 0, it's two equations. One for the real part and one for the imaginary part. Okay? So these are two equations. How do I get it? So I can write djh hr equals to 0 and djh with respect to hi equals to 0. So I have these two equations. So I can write here, I can replace, instead of h, I can write hr plus hi, and so on, and then have these two equations. So if I give you time, you will be able, of course, to do it. But it's, even for this simple problem, it takes time and it's cumbersome. Alternatively, maybe I will send also some text about it to prove. I will check, okay, if I have it. So instead of this, there is an alternative way. When you have a function of a complex number, you can write it as j, h, and h complex conjugate. And then you take the derivative with respect to complex conjugate and equate it to 0. And you assume that h and complex conjugate and h are independent. Okay? This is a mathematical trick. And I will send also this, so I need to remember two things. Okay? To send you some material from textbook about this. Also, it's important to know. Because this makes our life, these are two equations, right? Because complex. Complex equals to 0. These replace these two equations, which makes our life much easier. Okay, so let's do it. So we can write the dh conjugate of, let's write it as a function of h and h complex conjugate. So we can write it like this. 1 minus h multiplied with 1 minus h complex conjugate phi x plus h complex conjugate phi v. Okay? So this will be, okay, so I assume that H and H complex conjugate are independent. So I have minus 1 minus H phi x plus H phi v equal to 0. Okay? So from here, I get what is H, which here it will be, okay? I will write it here. Very easy, and remember that generally it's a complex, but here I get for this problem a real number. So we get H phi x divided by phi x plus phi v, which in this case the solution is a real number, but I didn't make that assumption. Just I found the derivative and equated to 0. So if you try to work with these two equations, you will see that even for this simple problem, it takes much longer time and effort to do that. So this trick, which can be proved mathematically that it works, and it's important to read why we can do that. Either you read it on textbook, or maybe I will find some material, you know, maybe 2 pages. It's important to read this stuff to understand why we can do that, because it's beyond that. Complex numbers. Any questions so far? Okay, let's continue. Okay. So also for the mean squared error, we have 2 different definitions. One is the narrow band, and one is the broadband. And the broadband MSE, somehow, okay, I'll work from here somewhere. Okay, and the broadband MSE, this is the narrow band MSE, just like we said, this is the definition. And we can also have the broadband MSE, which is simply the integral. Where is that? Here. This is the broadband MSE. So it's the integral of the narrowband MSE. Because the mean squared error, we find what is the mean squared error for each frequency, and we take the integral over all frequencies. So if we find H for each frequency independently that minimizes the narrowband MSE, necessarily the vector H that we found will minimize the broadband MSE, obviously. Okay? So what we find here, it also minimizes the broadband MSE, because we can work on each frequency according to our model. We work on each frequency independently, and then the broadband MSE is an integral of the narrowband MSE. So if we minimize each one individually, and of course each term of the MSE is positive number, so if we minimize this integral, we minimize the total integral. Okay, obviously. And also the broadband MSE is a summation of 2 components, one which is associated with the distortion, and one that is associated with the residual noise. Somehow it doesn't work. We'll, after the break, we'll try to fix it. Okay. Any questions? So we define performance measures. Now we can find the optimal gains. So the optimal gains the Wiener filter. We just worked on that. So we can find it also from here, which is the derivative using the expectation. Also, we can find it from here. And then we have the Wiener filter that goes like this. Okay, this is an alternative way, which is also a way to work on that. How do we work on that from here? Okay, so I will show you an alternative. Instead of this, what is the mean squared error, JH? We can say that JH is the expectation of the error, which is HY minus X magnitude squared. Okay, here we found it as a function of variance of X and variance of V. But we can work directly from here, from the definition. Also, it's fine. Okay, so if we open that and we write y equals to x plus b, we get this one. But we can work from here. And now, if we want to find the derivative of this with respect to h, we need to write it as separately as h and h complex conjugate, which is hy minus x multiply with complex conjugate of h, y minus x. Okay? So if I take this derivative of j, h complex conjugate with respect to h complex conjugate, we have it only here. So it will become, as expectation, okay, the derivative goes inside of, let's write it like this, y complex conjugate multiplied with h y minus x. And we equate this to 0. Okay, so this is what we have. And then if we put it inside, so we have h variance of y, because this and this variance of y equals to cross variance or covariance between x and y. And if we, so we can find that h is the covariance of x and y divided by phi, which is the same as this. Why? Because y is equals to x plus v, and v is independent of x, so they don't correlate, so it becomes like variance of x. This is the numerator, and the denominator, which is phi y, variance of y, which is the summation. So we get the same solution. So we get the Wiener filter. So this is the Wiener gain, which is the input SNR divided by 1 plus input SNR. So remember when we ask about that when the input SNR increases, we want to have higher. So if the gain is between 0 and 1, we want the, when the input SNR is higher, it means that we want to keep the signal undistorted in those frequency bands. For frequencies when the signal narrowband input SNR is high, we want h, the gain in those frequencies, to be higher or closer to 1. When the input SNR in frequencies, the narrowband input SNR is low, h will become lower, closer to 0. So we see that the Wiener filter behaves like that, which makes sense. If it didn't behave like that, then something is wrong. Then it doesn't make sense. Okay? Okay, so we can write the Wiener filter also using the magnitude squared coherence function. So I will define it immediately in the next slide, but before that, magnitude squared coherence function, it means how x and y are correlate. How do they correlate? So if x and y correlate, high correlation, it means that the input SNR is high. So you see that the Wiener gain is simply the magnitude squared coherence function between x and y. And it's 1 minus the magnitude squared coherence between v and y. Okay? So if v and y have low coherence, it means that the noise is low. So the input SNR is high. It is the same. So it's also possible using this relation. And the definition of the magnitude squared coherence function, if you remove the magnitude squared, so this is the coherence function. So it's actually correlation between two samples, complex samples. So we take x, y conjugate, complex conjugate, and we normalize it by the variance. And also we can do it for the noise, how it looks like. So these expressions are easy to obtain. Okay. We can also define something which is nice. You see the coherence function is a real number, right? So we can define a complex coherence function between x and v. And this complex number, we can define it as the coherence between x and y plus j, the coherence between v and y. So we can write this, so you know that this is the magnitude of this, the magnitude squared of this, plus the magnitude squared of this equals to 1. Under our model that, you know, this is the model. So since this is the model. So in our case, since this, the magnitude squared of x and y, plus the magnitude squared of v and y equals to 1, we can define an angle, which we call it theta for each frequency, such that we define theta such that this will be cosine theta, and this will be sine theta. It's allowed. Why? Because the magnitude squared of this plus magnitude squared of this is 1, so we can define theta such that theta is between 0 and 90 degrees. Okay? So we can define theta between 0 and 90 degrees, pi over 2, such that theta is defined such that cosine theta for frequency, certain frequency, narrowband, equals to coherence between x and y. Okay, so this this value, the magnitude of this, is between 0 and 1. But also we know that their summation, this summation is 1 because this is our model. Okay? Why do we need it? So the way we need it is the definition. Okay, we can define this theta, but also for when we want to represent signals, sometimes we represent signals as vectors. So suppose that we have a vector, x. This is the desired signal. And the noise is uncorrelated with the signal. So it means that the noise is like this. I can write it like this. This is the noise. is uncorrelated. So we have here 90 degrees. When we have two vectors uncorrelated, so signals, we say that they are uncorrelated, so we have 90 degrees between them. And then we can represent their summation. Y, x plus v, and this is the angle, theta. Okay? So this says, this represents how x and y correlate. So what is the angle between the desired signal and the noisy signal? So it's just like a graphical representation of signals. And you can represent signals this way. It's more like a convention. So when theta is small, we see that y and x are more correlated. When theta is large, it means that they are less correlated. Also, we see that when theta is small, the noise is small. So the input SNR is high. When theta is large, closer to 90 degrees, we see that the noise is large. So the input SNR is lower. So it's a nice way to present signals this way. So we can write also the Wiener filter using this convention and parameter. So we can write it that H, the Wiener filter, we can write it as cosine squared of theta, which is 1 minus sinus squared of theta, using this definition of theta. Okay, so I can ask you, what is the definition of theta, and to represent it in a graphical way for signals like that. So if the noise and the desired signals correlate, we can also define. So it will not be 90 degrees. It will be some angle between them. Okay? And then we have summation. So it's a nice way to visualize dependence or correlations between signals. Okay? And then we see that if theta goes to 0, okay, it goes to 0, what does it mean? That the input SNR is very high. It goes to 0. So the noise is small. So it goes to 0. And H of cosine squared theta goes to 1. And when theta goes to 90 degrees, the SNR, so cosine squared, goes to 0. So it's a nice way to show it. And also we can see some examples like this. We can also present the MSE and see some relations, and we can also write the other performance measures, the noise reduction factor, the desired signal reduction factor, and the distortion index as a function of theta, which is nice to show. It's a more compact way to present it. And also we can plot the Wiener gain as a function of the input SNR. So this is the plot. You see when the input SNR increases, it becomes closer to 1. When it decreases, it becomes closer to 0. We can also plot theta as a function of the input SNR. You see, when the input SNR is high, which means that V is small, theta goes to 0. Theta goes to 0. When the input SNR is low, it goes to 90 degrees, pi over 2. Okay? And we can also plot the noise reduction factor, the narrow band, as a function of the input SNR, and the distortion index as a function of the input SNR. See, when the input SNR increases, using the Wiener gain, the distortion decreases. And a nice property that we obtain the Wiener gain based on the MSE, the narrow band MSE. And then I can ask you, what will happen with the broadband output SNR? So it can be shown that the output, broadband output SNR, is not smaller. It's always larger or at least equal to the input SNR. So the Wiener, just like we know in the time domain. So the Wiener gain, always we can get some, at least 0 gain in broadband SNR. And there is a proof for that. Okay? I will not go into the details, but here is the proof. We will take 10 minutes break. I will talk about specific example and using the Wiener gains to enhance signals with certain spectrum. Okay. Any questions? Okay, so now it's like 11:13. Let's have 10 minutes break. It's tea break, right? So enjoy your tea, and then we continue. Intuition behind it. So suppose that we have this kind of signal. Okay, so this is the variance of the signal in the Fourier transform domain, which means that this is actually the spectrum of the signal. Okay, so suppose that the spectrum of the signal is constant for frequencies smaller than quarter, and then 0 otherwise. So the spectrum of the desired signal as a function of f, this is the spectrum from -half to half, okay, because this is the Nyquist frequency. So this is the range. So it goes like this. This is the spectrum of the desired signal, which means that it contains also in the low frequencies. We don't have for the desired signal high frequencies. And suppose that the noise, the spectrum of the noise, which is the variance of V for each frequency, the spectrum of the noise looks like this. Okay, so it's better. This is like a normalization, and it goes like this. This is the spectrum of the noise. Here is better. Okay? So this should be a straight line. Okay? Like this. Okay? So any filter that you will choose, meanwhile we talked about the Wiener filter, but actually any filter, its objective is to reduce the signal distortion, the desired signal distortion, and to suppress as much as possible noise. So in this high frequency range, see, like in this range, of course, we can cancel the noise completely, obviously, because we don't have desired signal in this frequency range. In this range, what will be the gain? So if I try to plot the gain for all frequency. Okay, so it will be here. Okay, so the gain here, of course it will be 0, because we don't have desired signal here. What will happen here, in this area? How does it look? Look like this, how does it look? Okay, so we need, for the Wiener gain, if we try the Wiener gain, or any gain actually, it means that when the signal to noise ratio is high, the gain will be higher, and when the input SNR is low, the gain will be lower. Any gain, okay? And the Wiener gain, actually, we know that it looks like input SNR divided by 1 plus input SNR. because we obtained this. But actually, any gain, when the input SNR is high, it will be higher. So at this point, for 0, you see the SNR is lower, and it increases when we come here. Okay? So it can be something like that. Okay? So I don't want to show exactly the structure, but probably it will look like this. You see this number, and so it can go up and then go to 0. And of course it will be symmetric. Okay? Because here it will be lower, and then it goes up, and then here it will jump to 0. Any gain, and specifically the Wiener gain also looks like that. But if we want to find the exact expression, what we need to find is the input SNR, which is the ratio between the spectra, okay, like this divided by this, and then to use it as input SNR and to put into this expression. Okay? So this will be the input SNR, the ratio between the variance of X and the variance of V, and then we have mathematical expression, like this. And if we take, this is the narrow band input SNR. If we take the broadband input SNR, since the integral of the total integral of the variance of X, total spectrum, and the total spectrum integral over the spectrum of V, and for this example, we get alpha divided by beta. And then we have this expression for the Wiener filter. You see that it's 0 in this range, high frequency range, because we don't have this art signal. How does it look? So if we plot the gain in SNR for using the Wiener gain as a function of the input SNR, so the gain in SNR decreases. First, when the input SNR increases, the noise reduction decreases. This is always true. You see, because when the input SNR increases, we have less noise to deal with. So the noise reduction decreases, and then the gain in SNR also decreases. The MSC also decreases because we have less distortion. We reduce less noise, so we have less distortion and less mean squared error. So this plot makes sense. The trend makes sense. The exact plot depends on which filter we use. Okay. Let's see another example. Instead of the first example, let's talk about another example, that sinusoidal signal, see, like this. And suppose that we measure this signal on a certain interval, which means that we have only capital T samples of this signal. The amplitude is fixed, the frequency is fixed, the phase is random between 0 and 2 pi, and we measure just T samples, capital T, of samples of the signal. And suppose that we have additive white Gaussian noise. And this is more practical because we use, in the time domain, we used a fixed length filter so we can move it in real time, so on. But here, if we work in the frequency domain, we cannot do Fourier transform on infinite length of the signal. We need to restrict the length what we measure. So suppose that we measure a certain length signal. How do we deal with that? Okay, so this is the time domain signal. Here in the first example, we specified the spectrum of each signal. Okay, so the spectrum of the desired signal, the spectrum of the noise. Here, because it's given in the time domain, we need to move to the Fourier transform and find the spectra, okay, of these signals. So what do you think? What is the spectra of white Gaussian noise? What? Constant, okay. Let's see. Let's see if it's constant, okay? What about this? It's a sine trend. It's a sine or cosine, that doesn't really matter. If you have a single frequency, what is the spectra? Of a pulse, okay. Okay. So I agree with you if the signals are with infinite extension. Okay, from minus infinity to plus infinity. But because we are looking for truncation, specific length of measurement, so it's not exactly. Okay? So if we have window of length capital T, a certain window of measurement, we multiply this window with either a pulse or a constant. So in the in the frequency domain, if we have in the time domain multiplication, what do we have in the frequency domain? Sync, which is the convolution between the Fourier transform of each. Okay? So because we have a certain measurement, so we have a sync. We will see that it's not exactly a sync because we have a certain length, so it's a periodic sync, which is the Dirichlet function, okay? And then we have a periodic sync, Dirichlet function, convolution with a spike, or with a constant. So let's see. So these small details are important when you solve problems or you deal with problems. So let's move on. Okay. So first, regarding the spectrum of the signal. Okay, so let's talk about the Fourier transform of our signal, xt. So xt is a sine function, like this, and we compute the Fourier transform at a certain length of the signal, from 0 to t minus 1. So we have capital T samples of the signal. So if we compute it, we get this. This is the Fourier transform, which is exactly the Dirichlet function, Dirichlet kernel, sine tx divided by sine x, which is similar to the sync, but it's not sync. It's periodic sync. Okay? You see? So this is the Dirichlet kernel convolved with the impulse. Okay? So we get this. This is the Fourier transform of the desired signal. Okay. And this is, so the variance, you see, so the variance of the desired signal will look like this, or the spectrum of the desired signal. So you see you have, this is similar to sync, but it's not sync, it's like the periodic sync, which is centered around F0. And another one centered, this is centered around F0, and this is centered around minus F0. Because you have the two frequencies, the positive and the negative. Okay? This is the spectrum. So it's not just two pulses, it's around each pulse we have the Dirichlet kernel. And the Fourier transform of the noise, of the white Gaussian noise, but it's with a certain length of the signal. So it becomes, if we compute the Fourier transform like this, so it's a constant. Okay, it's a constant with the variance. But this constant you multiply with t, the length, the number of signals, the number of samples. So the input SNR is the ratio between the variance of x and the variance of v. So we get this expression, which is multiplication with a certain constant of the Dirichlet that is centered around minus f0 and plus f0. So this is the input SNR, and we can use the input SNR to compute the Wiener gain. So what we see is that this Dirichlet kernel, it goes to 0 very quickly around the pulse. Okay? So this is the broadband input SNR if we want to compute it. It's just the integral of phi of the variance of x divided by the integral of variance of v, and we can compute the broadband input SNR. And if we talk about an example where the amplitude of the sign is 0.5, f0 is 0.1, and we measure 500 samples of the signal, of the noisy signal. So here we see the gain in SNR, the MSE, the noise reduction factor, and the desired signal reduction factor as a function of the input SNR, using that is obtained with the Wiener gain. Okay? So we see the trend. Of course, the noise reduction decreases, the gain decreases, the MSE decreases, and the distortion decreases as we increase the input SNR. But if you remember, we did something similar in the time domain using a filter of 30 samples. Here, when we go to the Fourier transform, we work with a whole signal of measurement of 500 samples. So we can obtain a better performance. Okay, so here we see a realization of the signal. So this is a realization of the noisy signal. So you see these two spikes. So it looks like spikes, but it's not exactly spikes. It's a Dirichlet kernel around each point. So if we take, this is the magnitude of the spectrum of the noisy measurement. So you see we have this this is for the positive frequencies, this is for the negative frequencies. So we see that we have a frequency that is high, this is the desired signal, around 0.1, frequency 0.1. So after we apply the Wiener filter, we get this. This is the spectrum of the estimated signal. This is the signal in the time domain, the inverse Fourier transform of y, and this is the signal, the estimated signal in the time domain. Okay, so we see here nice thing. If you compare it to the Wiener filter that is obtained in the time domain, here it's much better. Why? Because we used 500 samples, and we used the Fourier transform over the 500 samples, and we applied the Wiener gain in the Fourier transform. So it looks much better if we compare it to the time domain. Over there we worked with short length filters of 30 samples. Here it's much longer. But beyond that, I want to discuss with you what kind of information did we use to obtain this estimate, these gains. So we assume that for each frequency, we know accurately the input SNR. It's not obvious to know the input SNR. Usually we need to estimate that. Okay? But once we know accurately the input SNR, you see, we were able to clean the noisy measurement, and we could obtain a quite clean, you know, it's not perfect, of course, but it's very nice looking spectrum of the desired signal, if we know the input SNR. But it's not easy to obtain input SNR. So when we work with the short time Fourier transform for speech enhancement, when we continue and we reach speech enhancement, you will see, so you can record your voice, you add some noise, even white Gaussian noise, and then to know for each frequency and each time bin in the STFT, to know the signal to noise ratio, it's problematic. Of course, if you know the clean signal, you can you know the input SNR for each time frequency bin in the STFT domain. But of course, you don't know the clean signal. So even if the noise is stationary and white, like white Gaussian noise, even then, because the desired signal is non-stationary, it's very difficult to know for each time frequency bin the input signal to noise ratio. Okay? So this will be the example that you will work on for speech enhancement. It will give you some practical challenges, how to do signal enhancement, even for single channel. Okay? But here, so, okay, so let's continue with the trade-off gain. So the trade-off gain, also similar to the time domain, but instead of working with the MSE, we define a different problem. We try to minimize the MSE-based signal distortion, okay, JD, because we know the MSE is composed of two components. One is related to the signal distortion, and one is dependent on the residual noise. And we try to minimize the distortion, MSE, subject to the noise-related MSE will be Aleph, where Aleph is a parameter, multiplied with the variance of V. So to solve this problem, we can use Lagrange multiplier and choose this Lagrange multiplier such that the constraint is satisfied. Or we can keep the Lagrange multiplier constant and play with that. We can keep it a constant for all frequency, or we can change for each frequency this Lagrange multiplier, whatever you like, so that this constraint or requirement will be satisfied. And so here we get, you see, so it's equivalent to multiplying the variance of V with the parameter mu. So if mu is larger than 1, it means that we give more weight to the variance of the noise. It means that if mu is larger than 1 in that frequency, okay, so in that frequency we will reduce more noise. But if we reduce more noise, the distortion also will increase. It comes together. Suppressing more noise increases also the distortion. So we have this expression, and vice versa. So for each frequency, by controlling this parameter mu, we can control the trade-off between noise reduction and signal distortion. Okay, in some frequencies, if we want to reduce more noise, we can increase the signal distortion. If in some frequencies we want to reduce less noise, we can change mu for each frequency. And we can change, of course, mu such that the constraint will be satisfied So we get, you see, in the time domain, for examples, we had to do it numerically. Here we can get this expression. So we can obtain mu such that the constraint and the noise, residual noise-based MSE, that it will be satisfied. So we have nice relation between mu and aleph. Okay? So if we want, actually, if we want that this narrowband constraint will be satisfied, it means that the gain should be square root of aleph. So it's very obvious. We can also talk about the magnitude squared coherence function between x and f plus. So when we talked about the Wiener gain, we talked about what is the coherence function between x and y. Here we define something different. We define x plus square root of mu v. And then we define the coherence between both of them. And then we can write the trade-off filter as the magnitude squared of this coherence function. And it makes sense, right? So if I plot it, if I give a representation like this, okay, just like what we did, this is with the Wiener. With the trade-off, what did we do? We tried to minimize the mean squared error with the parameter mu. Okay, so instead of minimizing the j that looks like jd plus jn, what did we do? We put here a weight, mu, right? And then we give, if mu is larger than 1, we give more weight to this part. And then we are able to reduce more noise if mu is larger than 1. So you see, this is mean squared error, which is equivalent as multiplying the noise with the square root of mu, increasing the weight. So if we give a graphical representation of this problem compared to the Wiener problem, so we have x, and here we have square root of mu multiplied with v. Okay, you see why? Because here we multiple mu with something which is square root, mean squared error, which is, we have here something which is related to v squared, mu multiplied with v squared. So it's similar like multiplying v with the square root of mu. So we can define here theta with the parameter mu. So this is the, so this will be x plus square root of mu v, and this is theta mu, which is the angle between these two. Just like what we see here. Okay, so this is the angle. I will define the angle immediately, but we look for the magnitude squared coherence between x and x plus square root of mu v. And this is actually the gain of the trade-off filter. And we can define this angle. Okay, so this angle. So we define it like this. So this is the coherence between x and x plus mu, square root of mu v, plus j, the coherence between v and x plus square root of. You see, instead of y, we write x plus square root of v, because this is the new. We want to give more weight to the noise. And this will be defined as theta mu. And we see that we can define, we can obtain the trade-off gain as cosine square of theta, just like we did with the Wiener gain. So it's just like extension from the Wiener, where mu equals to 1, to trade-off. The parameter mu controls the trade-off between noise reduction and signal distortion. And we have specific expressions similar. You see, instead of theta, that was for the Wiener gain, we have theta mu. That is for the trade-off. See, it's very, very nice relation. Let's see what is the effect of mu on the performance measures. So here we see, we go to the previous example, and then we apply the trade-off filter. So we have the noise. Let's see about the noise reduction, okay? So the noise reductions, we have for different mu. Here, the red one is mu equals to half. The blue is mu equals to 1. Mu equals to 1, which is like the Wiener. Yeah? The green is mu equals to 2. And then this one, mu equals to 5. So you see, when we increase for a given input SNR, when we increase mu, we give more weight to the noise. And here or here, we give more noise. We give more weight to the noise. Error. So the noise reduction will increase because the trade-off filter would like to reduce this part. But then it will come at the expense of higher distortion. So you see, when the noise reduction increases, also the distortion index also increases for a given input. The gain, what happens with the gain? Okay? So when we increase mu, the gain decreases. Because when the gain decreases, it means that we suppress more noise for each frequency. If we suppress more noise, it also may affect, or it affects the distortion. And this is theta. So when mu, you see, when mu increases, this part increases, so theta increases, theta mu. So if we plot theta mu as a function of the input SNR, so for a given input SNR, when we increase mu, you see, when we increase mu, theta mu increases, just like this graphical representation. And we have the property that for any mu, no matter any positive mu, not only for mu equals to 1, any positive mu, we have the output SNR, which is at least as the input SNR. So the trade-off filter, just like we know in the time domain, the trade-off filter improves, or at least does not degrade, the signal-to-noise ratio for any mu. And the proof is just like for mu equals to 1, well, for the Wiener, but you change, you multiply. Okay, so you can follow the proof. Any questions on this example? And the trade-off and the Wiener. So we learned about the Wiener and the trade-off. Let's see. Yeah, question? Okay. Somebody ask a question? I hear something? Oh, okay, sorry. Okay. So let's see another example. Let's go to the first example that we saw at the beginning with the spectrum of the signal, this art signal, this, and the spectrum of the noise, like this. So suppose that we have this example, which we said example number 1. Let's see plots of the gain in SNR using the trade-off filter, the MSE, the noise reduction factor, and the desired signal reduction factor for different mu. Mu equals to half, 1, 2, and 5. Okay, red is half, blue is like the Wiener, mu equals to 1, this mu equals to 2, and 5. So we see that for this example also, for a given input SNR, so for a given input SNR, when we increase mu, the noise reduction increases. Similar to what we saw before, and then the gain in SNR increases because we increase the noise reduction. The distortion, we pay for that. So the distortion also increases. What happens with the mean squared error? So the mean squared error is minimal when mu equals to 1. Okay? So because when mu equals to 1, we have the Wiener filter, or the Wiener gain. And it's minimal when mu equals to 1. So you see the blue line is the lower line. The trade-off tries to trade off between noise reduction and distortion. But for the MSE, we obtain optimal solution with mu equals to 1. Now let's talk about parametric Wiener gain. So parametric Wiener gain, we can, now that we define, actually we can do even more than that, but this is, I want to give you some intuition and the things that you can do. Sometimes you find solutions, and then you can add parameters for the solutions and see how these parameters give you different relations between existing solutions as specific examples, and also it can add more flexibility in the solution. So here I can define something new. I can define a gain function that looks like this. And I can define it with two different parameters, mu1 and mu2, like this. And then you can ask, okay, why should I give it like this? And theta is just like what we defined here. This is theta. Okay? How did I define theta? Such that cosine theta equals to coherence between x and y. I can define theta. So I can write h, a new h, new gain, with parameters mu1 and mu2 that looks like that. 1 minus sine to the power of mu1 and all of that to the power of mu2. Now, if I choose mu1 and mu2 equal to 2 and 1, if I put here 2 and pull 1, what do we get? The Wiener gain. This is exactly the Wiener gain, because the Wiener gain, we wrote it as cosine squared theta, which equals to 1 minus sine squared theta. So specific parameters of mu1 and mu2, like 2 and 1, will give us the Wiener gain. But not only that, I can get, now I can, in the previous example, the trade-off gain, I saw what is the effect of mu, what is the effect of mu and the performance, and the gain in SNR, and the noise reduction factor, and the desired signal, the reduction factor, and the mean squared error, and so on. Okay? So I show what is the effect of mu on different performance measures. And you agree that if I increase mu, I increase the weight, and then I get more noise reduction at the account of increasing the signal distortion. Now, if I give you an expression like that, so I can ask you, what is the effect of changing mu1 and mu2? And also I can ask you, okay, what are the range of values that I can use for mu1 and mu2? So I can plot two-dimensional map of the values of mu1 and mu2 and find maybe specific examples, specific gains that are known in the literature for specific examples of values of mu1 and mu2, but also try to find what is the effect of these parameters. So this is a very conventional way in signal processing to work with parametric functions and ask about what is the effect of these parameters. With a trade-off, it's very simple. We have only one parameter. And then this parameter, we understood what is the effect of this parameter. Also here, we can put two parameters like this and ask ourselves, what is the effect of these two parameters? But first, if I give you certain specific cases, so if I plot, if I see a map as a function of mu1 and mu2, so if mu1 equals to 2, let's say here 1, here 2, here 1, here 2. So if mu1 equals to 2 and mu2 equals to 1, here, this is the Wiener. Okay, so we have the Wiener gain, okay? Wiener gain. Let's see about other special cases. So we can choose mu1 equals to 2 and mu2 equals to half here. And this is also something that is well known in the literature, and it's called power subtraction. Okay? This one is power subtraction. Let's call it. And if we choose mu1 equals to 1 and mu2 equals to 1, both equal to 1, here we have magnitude subtraction. Okay, so the power subtraction method and magnitude subtraction factor method and Wiener gain, they are all known in the literature. And we see that there are special cases of the parametric gain that it can be obtained with other values of mu1. And then we can ask ourselves, okay, we know about these three, but what happens? I can choose different values, and I can modify these parameters to obtain something, which is also a nice method to obtain different trade-offs. But here, if we just compare these three, it is well known that magnitude subtraction is more aggressive than the Wiener gain. And the Wiener gain is more aggressive than the power subtraction, which means that in terms of noise reduction, magnitude subtraction reduces more noise than this one, and Wiener more noise than the power subtraction. And so the one, this reduces more noise than this, and this more noise than this. But in terms of the distortion also, this distort more the desired signal because it reduces more noise than the Wiener. And the winner reduces more noise than the power subtraction, but also has more distortion. So we can play with that, but you can also choose other parameters, and you can get these relations between them, okay? So the magnitudes of the noise reduction that is obtained with the magnitude subtraction is higher than the winner and higher than the power. But the distortion, you see, is also, when the noise reduction is higher, the distortion is also higher. And the nice thing is that you can choose different parameters, but also you can find what is power subtraction, how is it obtained, how do you obtain the power subtraction. Okay, so let me, I don't know how much time do I have, so I can talk shortly. Okay, so I want to give you some information. Why do we call power subtraction this method? What does it mean? And what is magnitude subtraction also? Why do we call it magnitude subtraction? What is this method? Okay, the winner gain, we know. We obtained it by minimizing the mean squared error. Okay, power subtraction, this method is also well known in the literature. It means that we take this model and we say that we can write that the variance of y, you see, it equals to the variance of x plus variance of b. Right? Because this is the x and v are uncorrelated. Okay. So we can write it like this, that the magnitude squared of x, which is not the variance, it's not the variance, we can say it's equal approximately to phi y minus phi v. Okay? This is one step. So this is power subtraction. Power subtraction, because it's the power, the variance, the power of y, f. Okay, this is the first step. Let's move on. Because we want to find an estimate. Now, instead of writing this, we don't know the variance of y. We need to estimate it. So we will write xf hat magnitude squared. This will be an estimate. It will be phi, the variance of y, f, which we don't know. So I put it here, hat, because we estimate it based on the measurement, minus phi v hat, which we also estimate for measurement. But instead of just putting this difference, because these are estimates, so we don't know if this will be larger, necessarily larger than this. And this should be positive number. So we must add something, so we put here max between this and 0. Do you agree? I can do that. Actually, in signal processing, I can do anything that I want. But I need to check that it works. Okay? You can do anything. If it works, very nice. If it doesn't work, change it, modify it until something works. But I can try different things. Okay, how do I continue? So I can say you know what? An estimate of this can be like this. I will write xf hat equals to max yf magnitude squared minus phi v f hat. Okay? This is easy. I have the measurements. Regarding the noise variance, in many cases, many applications, it's also easy to find it because the noise is stationary. And maybe during intervals where we don't have the signal, we can estimate the variance of the noise. Okay? So this is called power subtraction. What is the gain? The gain for this power subtraction. How do we find the gain? I remind you, the gain looks like that. Okay, this is Z. Is HF multiplied with YF. So the gain is this ratio. So if I divide it by Y, okay, and if I assume that it's positive, it looks like that. But I don't have to assume that it's positive. Here it's squared missing. Okay? You need to correct me if there is some mistake. Okay? Here, so you have the squared here. So what I can do, how do I find it? Okay? So I need x, not the magnitude. So I can take x hat like this, square root of this, okay, this is the magnitude. Now I will take the phase of y because I estimate the magnitude and I take the phase of y, so it looks like this. Okay, so I got an estimate of x, the desired signal. So if I divide it by y, if I divide all this by y, I get the gain for the power subtraction method. So this is called power subtraction method. Something similar, it's going to be done also with magnitude subtraction. Similar approach. The noise variance is still what? Unknown. I said, but it's easy to estimate. Why? It's easy to estimate because many times you have the noise is stationary, and even if it's not stationary, maybe during pauses of the signal, and you know when you don't have the signal, so you can just take the variance and average it by using the noisy measurement, because the noisy measurement will contain only noise, so you can average that. Okay? So this is, in many times, easy to estimate. That's why I get it here. Of course, I cannot write V magnitude squared because I don't know it. So I take the average. Okay? So this is power subtraction, and it's well known, and we can write it similar like this with the parameters, but we can use other parameters. So if I go to the example here, I see that if we take the example, one of the examples before, and I compare this, the red, blue, and green, H. So I tell you, one of them is the Wiener, one of them the magnitude, and one of them the power. So you immediately know which one is which, because the magnitude subtraction is more aggressive, which means that H is lower. So the red one is magnitude subtraction. The blue is in between, which is the Wiener. And the green is the power subtraction gain as a function of the input SNR. So the noise reduction, when the gain is lower, you see you have higher noise reduction. More noise is reduced. But then the distortion index, the distortion is also higher. The more noise that you suppress, so with the magnitude subtraction you reduce more noise, but also the distortion is the highest. The Wiener is in between, and the power subtraction reduces less noise, but it also involves less distortion of the desired signal. Questions? Okay. No, it went back. Assignment number 2. Okay? So today I'll give you assignment, and tomorrow we'll talk about speech enhancement in the short-time Fourier transform. Okay? So try to do this assignment even today because it's simpler. Tomorrow it will not be mandatory, just for people who are interested to do some practical examples with speech enhancement. I think it's nice. Okay, so this assignment. So first you have a few theoretical problems. I think that just to work with simple examples like this. So you have spectrum of a desired signal like this, and spectrum of noise like this, which is white additive noise. And then I ask you to compute a few things: the input SNR, the Wiener gain. It's quite simple. And then to compute the broadband input SNR, and to compute the optimal Wiener gain. And show that the MST looks like this. I think here. Okay. I think it's quite easy. Okay, so it should take for you a few minutes, I think. Okay, it's quite easy. The second thing is with the MATLAB code. So I want you to generate figure 9 in example 4, what we saw before, and play with the parameters or change, do something else, and try to understand what you do. Okay, figure number 9 is this one. What we just compared, the magnitude subtraction, the power subtraction, and the Wiener. So take maybe other signals, maybe change the type of noise, do something, take a look at the code, the MATLAB code, play with it. Okay? And then here we have a table that compares this Wiener, the trade-off, and the parametric Wiener gain, how it looks like. So you can play. For example, number 9, instead of the magnitude subtraction, you can take different values of mu1 and mu2 to see what is their effect. How do they, either you can change the signals to see the effect of different values of mu1 and mu2, not only these 3 examples. Okay, whatever you like. So this is the second assignment. And tomorrow we will talk about non-stationary signals, so about implementation with the short-time Fourier transform domain. Okay? Questions? Okay? Thank you. Okay, so we passed the more than 1 hour, and it's okay. So you have now lunch break, right? So, by the way, if you have any feedback, comments, things that you want to change, even though, so maybe you don't need to write it every day, but if you want to change some things, so let me know. To modify things and so on. that and turn it off. Yes.